There are some important things to see. So let me go ahead and, before I start talking about this page, I am going to narrow it down. You might want to get out a highlighter. I think that's a really good idea because there's so many words in section 7.6. But the key ideas, there aren't really that many. So I grab out a highlighter and have it ready because I am going to try to focus your attention on basically just 3 different pieces of this, on 3 different key statements, even though it's all important. And as soon as you have your highlighter ready, let's go back and quickly hit section 7.5. I can keep this up for another couple seconds. Sorry, I heard some of you guys is like we weren't, oh my goodness, what is going on? Sorry. Somehow I went to the very end. I must have done page down. Whew. Let me freeze the screen so I don't make you guys seasick or something. I'm going to open up the book. So if any of you guys did start on section 7.5 last night and you have some questions, I heard someone talking about a circle this morning. I gave a hint for the circle, but that doesn't necessarily mean that you remembered it last night. So we can peek at homework really quickly, not to grade it or anything. It wasn't even technically due today, even though you should have been able to fully attempt it. But as soon as we cover 7.5, we will peek at 7.5 homework and see if there's something that you want me to talk about. And then I'll go ahead and focus your attention on these little pieces of 7.6 that I need you to see and I need you to get. And then we'll be good to go for both homeworks being due on Monday. I know that's a little rough, but guys, 7.5, it's not long, it's not hard, and it's just like any other section, this would have been one section. Like, oh, here's the basic idea, apply. Here's the basic idea, apply. I mean, that's every section. Just this one, they decided to make it into 2. So the differences. The differences. First of all, okay, I should have done solid up there, and I didn't. I did dotted, so we did change that. Second of all, I didn't show you yesterday how technically I was thinking through in my head, because there just wasn't time to be honest, but how I was thinking through in my head, let's get like the pink one, that when this one said greater than, green, red, when this one says less than or equal to 3, that I was thinking of shading below that whole line. Technically going on forever, but I mean on your paper at some point you have to stop, right? Like you can't just, I mean, I guess you could literally just, but eventually your paper runs out. So if worse comes to worse, I mean your entire paper could be shaded, but we're just going to show indicating everything below. I mean it keeps on going to the left, keeps on going to the right, everything below. That's for the red one. For the blue one, it was everything above, right? I want the big one. Okay, forget it. No. There we go. No. Sorry, I want the thick one otherwise. There we go. For the blue one, it was everything greater than, so everything above. But we talked about how greater than. Why are you yellow? Oh, there we go. And he's thin again. We should sue. Okay. Ha. All the x's that are above, when x is 3, x is 4, x is 5, x is 6, is going to be to the right. Okay. And then if I were to go green, there we go. This one's everything above that diagonal line. But you guys notice, like even in the picture over there, we tried to see what the colors were. We weren't even sure. I mean, there's still this yellow guy somewhere. I don't know, whatever. Long story short, there was that overlap like I showed. However, why were there, in the final solution, why were there holes? Why are there holes in the final solution? If you guys look at that final solution, that's over there on the right. Final solution, the overlap, that nice little triangle with the solid and the dotted and the dotted. Why are there holes at every single vertex? Why can the vertices not be a solution or part of the solution? If they were all equal to, they'd all be solid. Wait, but this one's equal to, good. He's equal to, but what's not equal to coming into him? This guy. So what's shared between those two? Will this guy who's not allowed to be on the line equal the point that's on the line? No, which is why I have to put a hole here And this guy, he's allowed to equal 2. I know, but he's not. And it's what they share. So since it's shared, that has to be a whole. And then, well, this one, neither one of them are allowed to equal it. So forget that. Like, there's no way. So if there were 2 or equal 2's, then they would come together at a solid point. If there were all 3 or equal 2's, then all the vertices would have been solid. But because 2 of them said, no, I'm not allowed to be there, well, then he's not allowed to be there, has to be a whole. He's not allowed to be there, has to be a whole. Does that make sense? So what are the vertices in each of these? It would be the point -2, 3, because what's shared between the blue and the red? Well, the blue and the red share this point right here, so that'd be when x is -2 and y is 3. But that's not an actual point. I have to make it a whole. So there's a vertex at a whole. And then let's see. X is -2. I know that for this vertex, which is also a whole. But I would have had to plug in -2 to green to figure out what that y is. So plugging in -2 to green, that'd be -4, which is how they got the point -2, -4. And then I know this one is y is equal to 3. So I could plug in y is equal to 3. But to see where it hits the green line, I have to take the y equals 3, plug it in the y spot, and solve for x. So then 3 plus 2 is 5. If you graph it carefully, you might be able to see them just by looking at it. But more often than not, you're going to have to actually be doing little baby systems of equations to solve for the vertices. Now, all of that we're going to have to deal with in section 7.6. So let's go ahead and get over to section 7.6 and be ready to start covering it. But I get it. Those of you that started 7.5, some of you have maybe not burning questions, but at least curiosities or a little bit of confusion for some of the homework problems. Anything you want us to look at? Kyle. Okay. 37 gives us a little baby system with 2 equations. If you haven't gotten here in homework, what would be a great idea? Back of your homework spiral, you can do 37 and have it ready to reference tonight or this weekend when you do homework, yeah? Just quick reminder. Back of the homework, any of this, like if you're ever not ready to go over questions, you don't want to mess up your notes by putting extra. You can put it in your notes, but I think, Kyle, did you say sketch? And then find the solution with the vertices or something like that? Okay. I would totally, at least for my purposes, I would get y by itself because we like y by itself a whole lot better because they're both lines. And I like lines to look like y equals mx plus b when I go to graph them. So getting y by itself, I would get y greater than -2x plus 2. Getting y by itself, I would get y less than -6x over 3 plus 2 over 3. Now I'm going to rewrite this because number 1, my marker started freaking out, and then number 2, you can simplify a little bit. So let's go ahead and rewrite this system over here. So we have y is greater than -2x plus 2. And then we have y is less than 3. 6 over 3 is 2, right? -2x plus 2/3. You guys don't have to worry about being able to do this with mental math. I just did it quick in my head because it's a homework problem. But hopefully, by the time you get there, you're able to actually do the steps to get y by itself on your own. I'm going to go ahead and color code. That way it just makes everything a little bit easier. We can come over here to a graph and start graphing. So then Kyle, whenever we face a line, we're going to go ahead and look at our intercepts first, right? Slopes. So when I go to graph the red line, I know it needs to be or equal to. I know it has an intercept at 0, 2. Oh, that's not red. Okay, well, there we go. Let's try again. There we go. Then I need to go down 2 over 1, down 2 over 1. Shading. Guys, what's my inequality of that red guy? So if I was just shading the red guy, there he is. But who else do I need to shade? Yeah, the blue one. So the blue one has an intercept of 2/3. Yeah. 2/3, I don't know, somewhere here. not quite 1, a little bit below. I need to go down 2 over 1, so down to negative 1/3, and down to negative 1 1/3, and over 1. Down 1, down 2, over 1. And you might think, well, aren't these parallel? Well, wait a minute. What are these two? Parallel. So I could go up 1, 2 over 1. The problem is, and it's not or equal to, so now it's also, even though it hits somewhere different, if you graph these correctly, it will stink. Hold on, shading. There could still be overlap. But what does this one say, the blue one? Less than. Now, if you guys don't understand the idea of below, like if this was a hill, below the hill, above the hill, wherever the hill is, like where would the ground be, where would the sky be? Ground would be down, below, above. You could always test a point, like I see 0, 0 is not on the line. I could always plug in 0, 0, and I would see true or false. Plugging in 0 actually gets a true, which means shade the side with the point. The whole side will be true. But the below also works. But what's the dilemma? What's my overlap? Nothing. How do we know that for sure? But they might intersect. They never will. Why? Same slope. They're parallel. They'll never intersect. And their shadings are going opposite ways. So therefore, the final answer, good question, Kyle, none. There's no overlap. There's no solution, so there are no vertices. Yeah, good question, Ben. Anything else you guys want to see from homework? 50, 50? Oh, 15. I like it. All right, I don't want to save it. This is probably the last question. Guys, this one just says sketch. It's not even a system. It's a singular one. So why on earth is Kyle stuck on this? What kind of equation is it? It's a circle. All right, x minus h squared plus y minus k squared equals r squared, right? Don't I know exactly how to draw this circle? By going to -1, +2 as the center, my hk, x minus h, y minus k. What's my radius if that's r squared? So I need to go 3 this way, 3 this way, 3 this way, 3 this way. Wait, was that allowed? Why was it not allowed? What kind of inequality do I have? Less than. So what's this need to be? Okay, now it's allowed. Huh. Pretend it's a prettier circle. That's gross. Anyway, circle. Yeah, I know. I agree. Where do I shade? Below. Oh? Use my trick, guys. Isn't the center inside the circle? Wait, what else is inside the circle that's way easier to plug in? 0, 0. I just like 0, 0 because he's really easy to plug into anything and everything. Guess what? If I plug in 0, 0, if he's true, where do I shade? Where he is, which is inside. If he's false, where do I shade? Where he's not, outside. Just plug in 0, 0. 0 plus 1 squared is 1, plus 0 minus 2 is -2 squared is 4, is 1 plus 4 less than 9. True. So guess who's a solution? And guess who else, or which other points will be solutions? All the ones that are with him on the inside. Nice thing with inequalities, it's either true or it's false. And the boundary is the graph itself. So either all the points are inside are true or all the points inside are false. All I have to do is test one, and I know true or false, shade or don't shade. Okay, 7.6. What are those key words? Highlighters at the ready. It's my turn to start coughing. What are those key words? Sorry, getting ready for normal pre-cal. The first one is objective. Ironically, not optimization, even though it's a good word. It's a great word. But optimization is actually not a key word for solving section 7.6. Objective is a key word. Objective is a key word. Constraints. Those are key. And then optimal solution must occur at a vertex. Test. That's basically it. Those are the 4 things you basically need to know. Objective function. Let me tell you what an objective function usually is. Well, hold on. You guys know the English word objective, right? The objective for an assignment, the objective for a class, the objective for a practice, the objective for, what's the objective? Kind of. Can anyone put that better? But yeah, I agree. It's the thing to do. The goal. That's exactly what I was looking for. Thanks, Lacey. It's the goal. It's what you intend to accomplish. It's what you want to find. The objective. So for instance, in the problems that we were just doing, for the circle problem, the objective just was to get the shading of the final solution. But the one before that, where we had a system of inequalities, the objective was to find the overlap to the 2 inequalities and find their intersections. They happen to have no overlap, no intersection, so no solution. The objective in all the 7-6 problems will either be given as a z equals or be given in words like, hey, this is your objective. And so sometimes you have to make your own z equals. But the nice thing is, objective for this section and for our purposes, we're always going to call him z. Why? I don't know. I think it's because we're definitely not using z because of yesterday. Remember how I said no 3-dimensional stuff? So we're not using z in the equations. Okay, fine. So we'll call the objective z. Whatever. The objective, the goal. If you want to write down goal, it's a great way of thinking about it. Okay. The constraints. The constraints. Are you ever constrained in any way, shape, or form when you're trying to get to your objective? Practice, the day before a game, you're supposed to go over this and this and this and this, and it rains, and you're in soccer. Well, maybe you still go out, but maybe practice is canceled. Well, you were constrained by. Or, okay, it didn't rain, or it did rain, you still practice, but you only have a certain time frame. That's a constraint, right? You only have so much time to try to be effective. That also like deadlines and assignments, and or teachers and the bell. Oh, that's a constraint, right? Maybe you're constrained by how many kids are in class today. Choir kids gone. My period 1 was missing 5 kids, and there was only a class of 14, 16. I was constrained by, well, stink, I only have some of my kids, so the ones that normally participate maybe aren't there. The ones that are louder at catching or quicker at catching my mistakes, maybe they can catch them. We still did a great job. I'm not saying that, but there were constraints by having fewer kids in class. Constraints. Mathematically speaking, in this section, guys, what are the constraints going to be? What's going to be constraining or limiting our options? The inequalities that we were just talking about from section 7.5. Oh, so 7.5 said, here's how you graph stuff and find overlap. Section 7.6 is we need those because those are the constraints. Those are the limitations that we have to consider when trying to meet our objective. Oh. Key to solving. The optimal solution. Who's the optimal solution? Isn't the optimal solution meeting your objective? Does that make sense? Maybe you guys haven't used optimal solution a lot in like everyday language, but optimal solution, like it's the optimum result. It's your desired meeting of the goal. Does that kind of make sense? Your optimal solution is meeting the objective. But what does it say, or where does it say these optimal solutions can occur? Must. Vertices. So here's the long story short. If optimal solutions can only occur at vertices, what we need to do is sketch the constraints, sketch what's going on as far as limiting our possibilities, and then consider, here's the long story short. Once we figure out who the objective is, and once we've found our vertices, as in the intersections from section 7.5, if they exist, we need to test every single vertex at the objective and ask the question, who wins? If you're a business, What do you want to happen with cost? To be at a minimum, right? You want your cost to be at a minimum. Now, hopefully you have constraints dealing with the quality of your product and the good care of employees and things like that. Like, hopefully you're constrained so you're not just like, I have zero cost. Well, you probably have zero product or you're a thief. But anyway, coming back. You want your cost to be at a minimum. But your profit, what do you want? To be at a maximum. So the goals are different depending on the situation. So when I say who wins, if you're looking at cost, you want it to be a min. You want it to be the lowest vertex when plugged into the objective. But if it's profit, you want the highest. So you have to pay attention to the problem, what they're asking. The steps just say basically how to go about everything I've just said. Sketch the region of the system of constraints, the feasible region, whatever, like it's the possibilities for us to consider. Find the vertices, aka if you want to put a quick note to yourself, remember the intersections. Between each of the different pieces to the system. And then number 3 says test. And if you want to think about it this way, you can go ahead and make a little baby table and say, who are all the vertices? And then what happens when you plug them in? Like an X and Y table. My vertices are going to be little X and Y points. Probably multiple ones. And you're going to be plugging into some sort of, ooh, here's snazzy math notation, a function in terms of both X and Y. The objective usually says, give me your X, give me your Y, and I'll tell you what happens when you're looking at cost or profit or other situations that might possibly occur. So, the easiest type of example has no words. You have no clue how this could possibly apply to real life. It just says, hey, guess what? Here's your objective. All right, I want that. What do I want that to be? At a max. Highest of that, whatever that stands for. How are you constrained? How are you limited? By this system. But there are no words. You have no clue what this could possibly be relating to. Why does it make sense in a lot of practical problems? And maybe some of you are like, I have no clue what's a practical application of this. Okay. But some of you might be thinking a bit of it. What could be a practical reason as to why x has to be greater than or equal to 0 and y has to be greater than or equal to 0? Any ideas? Maybe dealing with area? I don't think my brain would have gone there, Tony, because I'm looking more like an actual application. What if we're talking about what sport is softball practice? Sure. So we're getting out of our winter sports and into spring sports. Or baseball practice. There we go. Baseball practice. Okay. What if the coach wants to run so many X drills that take 3 minutes each and so many Y drills that take 2 minutes each? Now, I know. But I'm just trying to apply it. Most drills don't take 3 minutes. But so many X drills, so many Y drills. You want to do the most number of drills possible. Why would it make sense that x has to be greater than or equal to 0 and y has to be greater than or equal to 0? Can you do negative drills? How do you do negative drills? You make the coach do the drills? Anyway, don't do that. Coming back. You don't have negative. If x and y are objects, you don't have negative objects. So guess what's almost always true? Almost always true. Because we might not be talking about objects, we might be talking about money, and you can have negative money. It's called debt. But anyway, coming back. X and Y, usually objects usually positive. So here's the nice thing, guys. Whenever you see, I'm not even going to use any of my colors. Whenever you see something like x has to be greater than 0 or y has to be greater than 0, or you read a problem and you're like, negatives wouldn't make sense. Nice thing is, right away, you know, you're only looking in the first quadrant. Does that make sense? So for everything you're doing, if it's a practical word problem where x and y are objects, you don't even have to think about any of these quadrants because something would be negative. That doesn't make sense if x and y are objects. Now, hold on. But what else do we have besides those first two? Well, we do have this objective, this constraint. X plus 2y has to be less than or equal to 4. I'm not going to try to put that in the practice analogy right now, but we could figure out something that's like, okay, but you only have so much time with this coach in order to be able to do blah, blah, blah. Okay, I would rewrite this to be y is less than or equal to, you guys know what I'm doing when I get y by itself, right? I'm getting y by itself. Cool. Subtract x, divide by 2, so be negative 1/2 x plus 4 over 2 is 2. We could graph this guy. We could go up to Down 1 over 2, down 1 over 2, down 1 over 2. Why do I get to stop right now, even though usually for lines I keep going? Why am I just going to draw that? Oops, that's awkward. It doesn't matter anywhere else. Yeah, remember, I'm bound to the first quadrant. Why did I do a solid line? Or equal to. Or equal to. This next one, I could do this one too. I could solve for y. Now careful, there's a negative, so I would subtract the x, but divide by a negative. The inequality flips. Do this work. You don't have to do it mental math. It's okay. But I'm going to end up with a positive x minus 1. Wait, x minus 1, that's silly. Why would I graph that? Well, I have to get up to the first quadrant somehow. So up 1 over 1, up 1 over 1. Oh, look, they hit. Why am I not graphing down there? Because it doesn't matter. Oh, wait, what haven't I done? It's kind of messed me up a little bit. I haven't shaded, have I? Oh, stink. Okay, so blue is supposed to be below. I'm going to use a highlighter just because it's light, and if I dark. So blue is supposed to be below. The first quadrant. What's green to be? Above? Not actually. It's just here. What's above the green and below the blue and in the first quadrant? Do you guys see my little baby region? You see him? When I have my little baby region, everything is or equal to, so I'm allowed to look at, I have to look at each of my vertices. So remember, in order to figure out what's going on, I need to turn my vertices into what? The objective. The objective is 3x plus 2y. What's one of my vertices? 0, 0. Why? Because he's the boundary of the first quadrant. Can anybody see any other vertices, though?
1, 1.
Yeah, I think so. 1, 1, because they both hit there. I could go plug in and make sure I wasn't off. 1, 1. Wait, no, Kyle. 1, 1 is not 1. Isn't it 2, 1? Did I shade weird? What if you shade weird and you can't quite tell what's going on? What are vertices? Intersections. Do you guys see how one of them is going to be when x is 0? And who hits there? The blue guy, right? What happens if you plug in 0 to the blue guy? 2y equals 4y equals 2. That's one vertex. I have 0, 0. The other vertex is when y equals 0, this guy. And that's with the green guy. So remember, it has to be the overlap. When y equals 0, plugging into the green guy, x equals 1. So far I have, just looking at my zeros, looking at my intercepts, I have these guys. But I do have one more. Kyle, you're totally right. And it is out there. It's inside the first quadrant. But who is it an intersection between? These two. Hey guys, we got to find intersection. If y is by itself, can't we just set one equal to the other? So if it comes to worst and you can't quite read your picture right, you can go ahead and solve. And you can go ahead and add the 1, which would be what, 3? You can add the 1/2 x, which would be 3/2 x. Was this a pretty intersection? X equaled 2. I plug back in and do 2 minus 1 is equal to 1. Oh, there they are. I found my 4 corners, 1, 2, 3, 4. What do? I plug into z and say, hey, what's the z when I get 0? 3 times 0 plus 2 times 0 is 0, right? What happens when you plug in 0, 2? Well, that's going to be 0 plus 2 times 2 is going to be 4, right? What happens when you plug in 1? Well, 3 times 1 is 3 plus 0 is 3. And what happens when you plug in 2, 1? 3 times 2 is 6 plus 2 times 1 is 2. Oh, booyah. out of all of the infinite points possible in the first quadrant for this situation, meeting all of my constraints, still an infinite number of points, the optimal solution, the one optimal solution, is at 2, 1. Because that is the point, that is the vertex at which the optimal, or the objective, is highest. It asked me to find the max. It is the max. What would be the min? That one, 0, 0, just call off practice. Well, okay, yeah, that would be the min, right? But what was going on in this problem? No words. Hey, look, did we get this little baby region? Yeah. Okay, we did. And then we plug it in and then see which one was the highest? Oh, dear. What happened? Oh. Just kidding. Guys, are these the vertices? It's that picture. Are these the vertices? No. Read. Test some interior points. What are they doing? They're like, I don't trust the process. I don't think you're right. Oh, sweet. Thanks. You have an infinite number of points. You can make sure. What happened when they started testing points in the objective? Was anything getting to 8? Nope. We got to 6.5, but any point that you would have plugged in here with any decimal, any fraction, anything in here would always be lower than that. It's kind of crazy. There is a way to find an optimal solution. Now, there is something called a graphing approach, which is good and all, but it actually just kind of shows you a trick that can happen. I think I'm going to leave the trick off for now. Instead, I would rather us look at, those are the weird things that can happen. Let's save that for homework help. Instead, I want us to look at what this really could mean. Hold on. We're not even going to be able to solve the whole thing, but wait. Objectives and constraints. This is like a life thing. You have an objective, you have constraints. How do you deal with it? Now, we're able to deal with mathematically. The other one is more of like a life learning, wisdom, procrastination, motivation, parents helping, teachers helping. Okay, here we go. But this is math. Why? What's the candy guys making chocolate? Oh, he wants to maximize profit. Do you see it? That's the objective. He wants to maximize profit. What do we know about profit? These chocolate cream dudes, they get us $1.50 per box. So if I'm trying to think about profit is my Z. And I'm making $150 per box. Girl Scout cookies? Is this like a practical? Anyway, $150 pennies per box of, okay, fine, we'll call the creams X. And a box of chocolate-covered nuts yields, we'll call him Y, $2. But does this manufacturer have any constraints? The combined production level should not exceed 1,200 boxes per month. Its factories can't deal with more than 1,200. You see it? Oops, that's 12,000. Don't do that. Where do we get the next one? The demand for a box of chocolate-covered nuts is no more than half my choir kids. When you go sell chocolate, are there some that people like more than others? Same thing. Well, sorry, that's true. Girl Scout people. Anyway, we're done. Like some things more than others. The demand for nuts, Y, is no more than half the demand for X. Do you guys see how we're going to have a system? Now, with these huge numbers, do you have to graph it by hand? No. So why don't you get Y by itself, go to your graphing calculator, and then find the overlap. Maybe even use intersection feature on your calculator to find the vertices. And what are you trying to check at the very, very end? Has the best profit. Bye, cool kids. I'll see you later. Try them both on Monday. Bring questions. This is the end of chapter 7. Yes, because you selling negative boxes. You can have a surplus, but it doesn't mean you're selling negative boxes.